In this video, I'll be showing you how to calculate the reactions, the bending moment diagram, and the shear force diagram for a simply supported beam with a point load on it. And I'll also be showing you how the position of this load P changes the reactions, the shear forces, and the bending moment diagrams. So let's jump right into the problem. So this is going to be our problem statement. We have a beam with a span length of L. We have a pin support on the left side, a roller support on the right side, and we have a point load P at a distance of A from the left side. Let's try to solve it. So when we say we are going to be solving it, what we actually mean is that we are going to be analyzing it. And what we mean by analyzing is that we are going to be finding the reactions and the internal forces. In this case, I'm not going inside the internal stresses. That would be a separate topic. For now, we are just going into the reactions and the internal forces. And for the internal forces, we are going to be finding the shear forces and the bending moments at all the locations, which essentially is the shear force diagram and the bending moment diagram. Our primary focus for this video is going to be finding all these three things, that is the reactions, the shear forces, and the bending moments, and the diagrams of each. So let's start off with these. Now, to start off with finding all these, we have to first find out the degree of statical indeterminacy, which is also called as the structural redundancy. Now, this can either be 0, which would mean that it is a statically determinate structure, or it can be greater than 0, which would mean that it is a statically indeterminate structure. If you want to learn about statically determinate and indeterminate structure, I also already have a video on it. And if you want to learn it further, just leave a comment down below. To find the degree of indeterminacy, we simply have to find the unknowns and subtract knowns from it. Now, the unknowns would mean the reactions, and the knowns would mean the equations of static equilibrium. Now, this equations of static equilibrium for a beam would be dependent upon the force system. In this case, we are assuming that it is a coplanar parallel force system. What that essentially means is that all the loading is going to be downwards and in just this y and x axis. So this z axis is gone, hence the word coplanar and parallel, because we assume that only the loads are acting downwards. Now, this is an assumption that there are going to be no inclined loads, and essentially or generally in a beam, we only consider loads which are acting from the top. If we have a frame, we would have considered loads from different directions. But in general, for a beam, we consider that the loads are acting right at the top, that is just in the negative y direction or in the positive y direction for that matter. Hence, it is called a coplanar parallel force system. Because of that, what we get is that we end up only with 2 equations of equilibrium instead of all the 6. Now, the Fy equals 0 means that the structure is static. It cannot move in this direction. Hence, all the forces in this direction, this y direction, is going to be 0. Mz being 0 means that this structure cannot rotate in this direction. So this is going to be Mz, that is pointing outward. So if you use the right hand thumb rule, we can see that this Mz is nothing but Mxy. So we are going to be finding Mxy equals 0 just for the fact that it cannot rotate along this plane. So we now have 2 equations of equilibrium. Let's move ahead. So we can just fill in the equations of equilibrium. Now, for the reactions part, we can simply change the pin support and the roller support with reactions. Again, we are not going to be taking the component of this direction because we are assuming it to be a coplanar parallel force system. So in this case, we are just left with 2 reactions. So all in all, we get 2 reactions as well as 2 equations of equilibrium, thereby giving us a statical determinacy degree of 0, which essentially means that it is going to be a statically determinate structure. Now, quickly, I'll talk about what a statically determinate structure does. For a statically determinate structure, if we are talking about the analysis of the structure, we can use just the static equilibrium equations to fully analyze the structure. This is not possible in statically indeterminate structure. Right now, we are going to be using just the equations of static equilibrium to find out everything there is to know about reactions, shear forces, and bending moments. Now, when it comes to the internal forces, we also know that for a statically determinate structure, the internal forces, not the stresses, are going to be independent of the material property. That is, the shear forces and the bending moments which we calculate at different cross sections will be independent of the cross section or the material type itself. And finally, for a statically determined structure, no internal stresses can be developed without having external forces, which is not a case in statically indeterminate structure where due to just the change of temperature, internal stresses can develop. For a determined structure, this is not a case. So now that we know about the degree of indeterminacy, let's go ahead and start solving for the reactions. So for the reactions, we'll first need a free body diagram, and this free body diagram will be for the entire beam. Also, we'll be needing the equations of statical equilibrium, which is going to be this Fy and Mz being 0, and we'll use these in correlation to find out the reactions for the entire beam. So let's start off by starting off with the free body diagram. This is going to be our actual structure, or this is rather our actual structure. We have to first convert it into a free body. What that essentially means is that we have to get rid of these and change it to a force system. So what a free body essentially means is that it is only represented by forces at different locations, nothing of supports. So we have to get rid of the supports. Now we cannot actually get rid of the supports, but rather replace it with some kind of forces. In this case, the forces are going to be the RA and RB. So in this case, we are assuming that our left point is A and the right point is B, hence the reactions. So now this, what we are seeing right now, is the free body diagram for the entire beam. Let's try to solve it. We'll use the first equation of equilibrium, that is F sigma Fy equals to 0, which again essentially means that the structure is not moving in the y direction. So we have a parallel force system and we have a coplanar force system. So we are not moving up and down in the y direction. Hence, all the forces have to come out to be 0. So if we solve it, we get the RA, which is moving upwards. We take the upward force as positive. So RA in the positive direction, RB in the positive direction, minus P pointing downwards. So the summation of this is going to be 0, which essentially means that RA plus RB equals to P. Let's keep this value aside. Let's try to use the other equation of equilibrium, which is Mz equals 0. Now, when we are trying to find the Mz at any point, this should be considered at any point on the plane in xy. We did not do that in Fy. That was just because Fy is a directional thing. Mz would be taken around a certain point. Now we can take the value of Mz at any point. So we can consider the rotation of the structure at, say, this point. So this structure should not be rotating at this point. The structure should not be rotating at this point. The structure should not be rotating at this point. What we essentially mean is that the structure is not rotating. Now, when we talk about rotation, we talk about rotation with respect to a point. So in this case, we can take any point on the plane xy and the Mz should be 0 because the structure is static. Now, to make our calculations easier, we check the bending moments at support nodes because that minimizes the calculation of one extra step. So what that means is that if we are trying to find out the moment at this point, for example, we'll be using this RA value multiplied by this lever arm. Again, this P value multiplied by this lever arm and this RB multiplied by this lever arm. However, instead, if we try to find out at one of the points, it will essentially mean is that this point, or rather this force unknown, gets a lever arm of 0. That means this is essentially gone. We are just left with RA and P. So that is what we'll do. We'll start off with that. So we are going to be finding it at the node B, which is this node right here. Let's try to find out. So here we have the RA multiplied by this lever arm. So it has a lever arm of complete L. So RA multiplied by L. Now this is going to be in the anti-clockwise direction and P is going to be in the anti-clockwise direction. So P multiplied by the value of B. So what we end up getting is that RA multiplied by L equals P multiplied by B, which essentially means that RA is PB by L. Now let's keep it aside and let's use these together. So we had the first equation as RA plus RB equal P. Let's replace RA by PB by L and let's solve for it. So RB becomes P minus PB by L, which essentially becomes PL minus PB. We'll take the P as common. We get L minus B, wherein L minus B is essentially the value of A. So we get RB as P multiplied by A. So these are the two values which we are getting. For the RA, the value is P by L multiplied by B. So this RA is dependent upon this value B and this RB is dependent upon this value A. Now we could have done it from the other side as well. So if we try to do the same equation but try to find out the Mz at the node A, again we'll get the same values. So we have this RA plus RB equal P from the static equilibrium equation of Fy equals to 0. Let's try to solve it again. In this case, for this point, we are getting P with a lever arm of A. So minus P into A, we are assuming that the clockwise is negative this time, plus RB multiplied by L. So now this time, this force will be acting at this point with a lever arm of L. So P into A plus RB into L. We get the RB value as P multiplied by A. We get the RB value as PA by L. Again, we can plug it in inside this equation. So let's plug in the RB value as P into A by L. All in all, we are getting again RA equals P minus PA by L, which gives us PL minus PA. Taking P as common, we get L minus A. In this case, L minus A is going to be B. So we are getting the same values again as you saw. So these are the three equations which we have, RA being dependent upon B, RB dependent upon A. Now let's try to plot it in a graph so that we can better understand it. So let's try to create some lines and let's start off with that. So the first thing which we know is that the RA plus RB value is going to be P. What that essentially means is that the summation of RA plus RB at any point will be equal to the value of P. So what I've done is that I've created three lines. We have a value of 0, we have a value of P by 2, and we have a value of P. So this is the half of the location, and this is the entire P location. What this gives us is that if we plot a graph of P, this will remain static because this P value is not going to be changing. However, RA and RB will change because these depend upon this B and this A value. In this case, we are getting a value of RA greater than P just because this A is less than L by 2 and B is greater than L by 2. So since you can see at the bottom that A is slightly lesser than the halfway, so this RA value will increase because RA is dependent upon the other side, that is the B. Now, if we use the same concept and move P to the center, what we should see is that RA and RB becomes same. And that is exactly what happens if A equals L by 2 and B also equals L by 2. If you move it to the extreme left or at the end, you'll see that the RA rises. So just because of this effect of P moving towards RA, this RA will increase. However, this RB will decrease. And that is what we see. Moving to the other side, we'll see the same thing. However, this time RB will increase and RA will decrease substantially. For our simple case, we have this as the value of reactions. So now that we are done with the reactions, let's move on to the shear forces. Now what we are trying to do again in shear forces is that we are trying to find shear forces at all the locations inside the beam, which essentially means is that for a free body diagram, we have to take a part of the beam. Again, we'll be using the same equations of static equilibrium, that is Fy equals 0 and sigma mz equals 0. Now, when we are trying to find the shear forces, we are trying to find it at all the locations. Now, we are not going to be doing that for every location, but rather we are going to be trying to find it for a specific area, trying to find the curve of that area, and we'll plot the shear force diagram, which essentially will give us the values at all the points. So let's start off with that. Again, we have the same free body. Now, this is going to be the free body of the entire beam. Let's break it down because we need to go inside the structure to find out the internal forces, which are the shear forces and the bending moment. Now, in this case, we can use the free body at any point. So we can use a free body, which is just this much. So we can just cut it right here. And if we cut a beam at any location, there are going to be some internal forces which are there. Now, these values can be 0, these values can be greater than 0, plus, minus, whatever the case is. But in essence, there are going to be these values because, again, my sigma mz equals 0 and sigma fy equals 0 has to work. Again, that is because if my entire beam is in equilibrium, my part of the beam will be also in equilibrium. So this, just by creating a beam and not creating internal forces, means that there is only one force acting on it, and this can essentially go upwards, which is not the case. And to minimize that, we have to have some kind of forces and some kind of bending moment so that this value does not turn and move. So we can take a free body diagram something like this. We can take it something like this as well. But if we take it like this P value also gets involved. We can take it from the other side as well. We can take it beyond P, or we can take it something like this, where we are just talking about the internal forces. Now, in general, we should try to minimize the forces when we are calculating it. So from the calculation point of view, we'll start off with something like this, where we are just working with RA and MX and VX, and we'll move on from there. So let's use this, and we'll just be focusing on the shear force right now. So the value of VX essentially means is that we are playing with the shear forces or the free body diagram from right here all the way up to this point here. That is, the X value is going to be right from 0 up to the value of A. So up to here. So we are starting from here and we are moving this way. Now we are going to be trying to find out the shear forces with respect to this value x, thereby giving us a diagram, thereby giving us the values at all locations in a way. So let's start off. Again, we are going to be using the equations of static equilibrium, Fy equals 0, which gives us a value of Ra in the positive direction, Vx in the negative direction, thereby giving us Vx value as Ra. Now we knew Ra, which was our Pb by L, so we get the value of Px as Pb by L. Now in this case, if you are going to be plotting it with respect to this point right here where x was 0 and at the point A, you'll see that nothing really changes because this value of Vx is not dependent upon the x itself. So what we get at x equals to 0 and x equals to A is the same thing as Pb by L and Pp by L. In this case, the graph or the curve is going to be a constant. Let's take all these values and put it aside. So let's find out the shear forces at the other locations. So for that, we'll be using this free body diagram. In this free body diagram, what we are doing is that we are increasing x from this side. So x is moving from 0, that is right at the point here, up to b, that is right at the point here. That is what we are considering. Again, we'll be using the equations of equilibrium. Now we are using this free body diagram just because of the fact that, again, we are going to be working with only RB as the known and only Vx as the unknown, and we are not going to be dealing with the other p values because we do not want to make our calculations more difficult. So let's start off. Again, we get the value of Fy as Vx plus Rb equals 0. Again, if you're confused about the sign conventions of shear forces and the bending moments, do leave a comment down below. I'll make an entire video on it. Simply put, shear forces, if for the left part of the portion is going up and the right part of the portion beam is going down, it is considered as positive. That is why we have taken Vx as pointing upwards as positive. So we get a value of Vx plus Rb, that is this value Vx right here, and this force Rb right here, both going upwards as positive. So we get a value of Vx as negative Rb, which gives us a value of Vx as minus Pa by L. Again, this is not dependent upon this x value. Hence, for values of x equals 0, that is the rightmost point, and value of x equals to b, we are going to be getting the same values. That is Pa by L and Pa by L in the negative direction. Again, the slope is going to be a constant because these values are not dependent upon the position, that is the x. Let's keep this aside and let's try to plot it. We'll quickly create a few lines. Now, these lines will be representing the values of shear forces at 0, p by 2 and p, again in the negative direction minus p by 2 and p. For the left portion, or rather this portion up to A, we can plot a simple diagram which will look something like this. So the values will start from 0, but for the entire portion of A, the value was constant as a value of Pb by L. So from right here up to this point right here, we get a value of Pb by L. Now we are getting this value slightly greater than P by 2. That is just because we have the A value slightly lesser than L by 2 and B value slightly greater than L by 2. For the left side of the portion which we plotted, we saw the negative values. So it will look something like this. P multiplied by A by L and P multiplied by A by L. In this case, A is less than L by 2. That is why we are getting the shear forces less than P by 2. So this is the graph that we are getting. Now, if this load of P were to move right at the center, you would notice that everything becomes or comes in rather kind of an equilibrium, that is inequality. So now we are getting again the values of VA for this portion as P into B by L, which essentially gives us P into L by 2 divided by L. So this goes away, we get a value of P by 2. The same thing would happen right here. So we get exactly at the center where the values of shear forces are P by 2 and minus P by 2. Now if you were to take this load P at the extreme left, we are going to see a major increase in this V value for this portion. Similarly, for the right side, we'll see a value of increase for the B portion. Again, bringing it back to our original, this is what will happen for a general case where this is A and this is B. So this was the shear force diagram and the shear forces at all the locations. Let's move on to the bending moment diagram. We'll use almost the same things where we are going to be using the free body diagram, the equations of equilibrium, and we are going to be combining those to find out our results. Again, we'll start off with the same free body. This time we'll be working with mx also. So let's directly jump inside the mz value at 0. Now, ideally, we can use this mz again at any point inside this entire plane, but we should be using it at such a point where we need to work with minimum number of equations. So which will be at this point at x right here. So if we use it at this point x right here, this Vx lever arm goes away and hence the Vx is out of the calculation part. So that is why we have chosen it at the node x. Again, for the node x, we are getting Ra multiplied by this lever arm, which is going to be x itself, minus the mx. Now, in this case, it is minus just because our sign convention works that way for the hogging and the sagging bending moment. Again, if you have confusions, just leave a comment about the sign convention and I'll try to make a video on it. So this gives us an mx value of Ra multiplied by x, which ultimately gives us a value of Pb multiplied by x by L. So this is the value which we get. Now in this case, you can see it is dependent upon the x value. So at x equals to 0 and x equals to a, we are going to be getting different values. At x equals 0, this entire equation goes away. We get a m0 value of 0. And for the value at x equals a, we get a value of p multiplied by a multiplied by b divided by L. Now in this case, since we are dependent upon the first degree of x, so this is going to be a linear curve and we'll have it that way. Let's keep this thing aside. Let's look at the other way. In this case, again, we are considering our x values to be starting right from here and moving this way. So this is going to be our x from 0 up to a value of b. Let's start off with mz equals 0. Again, we are going to be taking it at this node right here so that we get rid of this vx value and we do not have to consider it. If we had considered it at somewhere at this point, we'll have to find out or use the Vx2. So in this case, we are getting an mx minus rb into x equals 0. We are getting mx as rbx, which is pax by L. Again, this is dependent upon the value of x. So for a value of x equals 0, at this point right here, the value is going to be 0. However, at x equals to b, we are again getting the same value. Again, this is going to be a linear curve because it is dependent upon the x. So let's plot this on the graph system. We'll quickly create our entire beam. We'll create a value of AB and let's plot it. So for the left side, we can see we have a value of 0. And for the A point, that is point right here on this A line, we get a value of PAB by L. Similarly, for the B side, moving from this side, we also get the same value. So if we plot it, we'll get something of a triangle like this, where we have the left side as 0, the right side as 0, and this value PA and PB by L is going to be the same as PAB by L. Now, it is skewed slightly to the left side and downwards just because of the fact that this A value is less than L by 2, which is less than B. Now, this graph falls on a parabolic curve. What that means is that if we change the value of P, this will fall on this parabolic curve. So if we were to bring our P to the center, this will move to the center of this parabolic curve, wherein we'll get a value of PAB by L as, so we have a PAB by L at this location. If this A goes L by 2 and this B goes L by 2, we're essentially left is, what we are left with is P into L by 2 into L by 2 divided by L. So we get a value of PL by 4. And that is what we are seeing right here. Now, if we were to move it to the left, again, it will fall on this parabolic curve. If you want to know why that happens, it is simply because it is dependent upon A and B both. Hence, we get a quadratic equation. Again, if you want to know more about it, just leave a comment down below and I'll try to make a video explaining why this curve is going to be a parabolic curve. If you move this load to the right side, we get a curve something like this. The values will decrease or increase depending upon where it is located at. For our general case, this is where we have it. So now we have found out everything. That is, we have completely analyzed the structure for reactions, the shear forces and the bending moments. Let's plot all these together. So right here or at the top, we have the value of reactions. Here we have the shear forces and this is the bending moment diagram. So for a load acting at P, which is acting slightly to the left of the half portion, we'll get an RA value greater than RB because again, RA was dependent upon the B, RB was dependent upon the A. Similar for the shear forces is dependent upon the RA and RB. So depending upon the values of RA and RB, these values are going to change. If we bring it to the center, everything comes into equilibrium. RA becomes RB, these shear forces become equal, and this value becomes at the center with a value of PL by 4. If you move it to the left, RA increases, thereby shear force increases and bending moment decreases. It will lie on this quadratic equation or the parabolic curve. To the right, we get this value. And in our general case, we get this value. So now you know how a simply supported beam behaves with a point load on it, where are going to be the shear forces, what are going to be the bending moments, what are going to be the reactions, how those values will change with respect to the position of the P itself. If you like this video, please do hit that like button. It really helps with the YouTube algorithm. Also, if you're not subscribed, do hit that subscribe button. And finally, if you have any questions about this video or you have any further suggestions, please leave a comment down below. I'll try to make a video on it. Thank you for watching this video. I'll see you on the next one.